Good afternoon, everyone. Thank you for being with us in person. Thank you for those of us joining us online through the streaming. Welcome to this anticipatory briefing. The title of the session is Made in Space. Anticipatory briefings are interactive sessions led by academics who basically explore topics from the GESDA Breakthrough Radar. I would appreciate if we could stop the phone calls right now. I'm sorry. Thanks. And so basically, we try to showcase the latest science and anticipate how these technologies are going to impact us in the next 5, 10 to 25 years. It's going to be 15 minutes presentation and then 15 minutes of Q&A. And so our next speaker flew all the way from California. She's an associate professor at Stanford University. She's also a principal investigator in one of the labs that has the coolest names, called the X Lab for Extreme Environment Microsystem Laboratory. Her research interests include the development of nanomaterials for extreme harsh environment, high temperature electronics for Venus exploration, which must be the coolest cocktail wine liner ever. Like, what is your job? Oh, I do high temperature electronics for Venus exploration. And she also does microgravity synthesis of nanomaterials. She's currently the co-editor of 2 technical journals, and her research has been featured in Scientific American, Space.com, and NPR. In this anticipatory briefing, she will explain how space exploration advances like the utilization of orbital resources is poised to become a new frontier of economic opportunity for the next 5, 10, and 25 years. Please help me welcome Professor Debbie Senesky.
Awesome. Thanks so much for the introduction and for having me. Again, my name is Debbie Senesky, Associate Professor at Stanford University. And today I'm going to share with you a topic I'm very passionate about. I spent a lot of my career on Venus-grade electronics and more recently very passionate about space-made materials. So the question that I'd like us to think about over the next 30 minutes or so is, can we make bigger and better materials in space? And so the sample you see in the tweezers there is a very small lab-grown sample of graphene aerogel. If you zoom into it, it's very irregular. And as you can see, it's very small in size. So can we overcome some of these challenges by manufacturing in space? So to set the stage, I want to go back in time to the Metal Ages. And so modern civilization has really leveraged the breakthroughs in materials. So in the Metal Ages, we made weapons, tools, even chairs out of copper, bronze, and iron. And the ability to control temperature enabled us to have these wonderful objects and advance our civilization. The Steel Age has revolutionized transportation and also building, construction. And so that changed modern civilization and was enabled by the ability to control oxidation. And we're in the middle of the Silicon Age. And so having chips or wafers made of silicon and very fine controlled features on those wafers, very thin metallizations, very thin pattern, as small as the nanoscale, allows us to have the computation that we leverage today in our civilization. And that was enabled by vacuum technology, the ability to control vacuum. And so the open question today is, what is next? What is the tool that we will use to enable advancements in modern civilization? And so I would like to challenge us and think about microgravity as now a tool to enable potentially what we may call the age of AI or the age of quantum, as we just had in our previous speaker. So let's go to microgravity. Microgravity is very different. Humans behave differently in microgravity. This is astronaut Christina Holtz, and you can see her hair, and when she shampoos it on the International Space Station, it's very different in comparison how she might wash her hair here on Earth. Also want you to focus on this water droplet. It's spherical in shape. And so the microgravity environment is wonderful because it offers, again, this wonderful tool that, number one, suppresses sedimentation and buoyancy. So this is something we are subject to here on Earth. Also, it suppresses contact with the container that it might be in. So you could see it's free floating. This ball of water doesn't need a container. So contactless interactions. Also, if we zoom in at the thermal profile on this ball of water, you would see it would be controlled by diffusion as opposed to thermal convection. And all of these features lay a footprint on the materials that we manufacture. And in fact, what we find is that if we use microgravity, we can suppress a lot of the phenomenon that we see here in gravity. So if we go back in time to the early 1970s, we were actually using microgravity to explore materials manufacturing, primarily on the Space Shuttle and also Skylab and the Apollo mission as well. So you can see a lot of the pinkish, light bluish bubbles there on this chart are based on experiments that were predating the International Space Station. So we have a total of 163 crystal growth experiments that were conducted in microgravity. But you can see in the late 90s, actually right when the International Space Station came online, those materials, semiconductor materials, crystal growth, so inorganic materials, started to taper off. And that's because the International Space Station is a crude environment. We have humans there, so we can't have the high temperatures, the high pressures required for the inorganic synthesis. But what we did find in those early studies is that we made bigger and better materials. So this is an example of a semiconductor crystal boule that was made on Earth and in space using the same conditions. And so what you'll notice is that they're bigger in size, so you have increased growth rates. And if you zoom into the crystal lattice, you'll also see that the crystal quality, the suppression of defects, is observed as well. So can we harness this wonderful scientific breakthroughs that we saw in the early 70s, right? Although it's tapered down, we saw this remarkable scientific observation. So in the next 5 years, are we able to harness that and leverage what we have before us? Right now, the cost of space flight is plummeting. As we heard in the session, the panel earlier today, the advent of reusable rockets is really enabling us to significantly reduce the cost of access to space. So today it is around $1,000 per kilogram to deliver a kilogram into space. And so in the next 5 years, we will go below $1,000, and that continues to taper down. And in the future, maybe if we have a space elevator, that number can get up to a few dollars per kilogram. So something to look forward to. Unfortunately, in the next 5 years or so, another big event will occur, the decommissioning of our beloved International Space Station. So this space station has housed thousands of experiments. Also, astronauts have lived aboard the station. And so this has been a wonderful platform for us to conduct a variety of space-based experimentation. A lot of them have been focused on biology and understanding the advent of advanced medicines and also the behavior of humans in prolonged microgravity environments. So this has been a wonderful platform for many, many researchers around the world. Also, it has been an international endeavor, and that's something that we hope we are able to expand and continue to build upon. So what happens next? What are we thinking about post-International Space Station? The commercial low Earth orbit, or LEO, destinations are slated to replace the ISS. So there are a few commercial companies that are looking to create commercial or private stations that will live in low Earth orbit, potentially opening up tourism. So maybe we'll have our vacation on Blue Origin's orbital reef. So this is an image of the Blue Origin's concept. Maybe we'll conduct more scientific experiments in this type of environment. And also this opens up the possibility for manufacturing in low Earth orbit. If we're able to design modules on these commercial stations specifically for manufacturing, perhaps some of those modules could be dedicated to those types of endeavors. And so this would disrupt the supply chain. So right now on Earth, a wafer might travel from Europe or Asia over to the United States and vice versa, traveling thousands of miles to conduct that supply chain from wafer growth all the way to printing and patterning. It's quite remarkable. And so what I'm offering is, can we think about now moving some of those processes up to low Earth orbit and tapping into, again, this idea of bigger and better materials, overcoming a lot of the challenges that we have in modern day semiconductors and other types of advanced materials. So the International Space Station is currently 250 miles above us, and maybe in comparison to how we transport products in our current supply chain, maybe that becomes better. So moving forward, what is the 10-year outlook? This is an image from Eric Kulu, who has a website called Factories in Space. You can check it out. Eric catalogs every single experiment that has been conducted in low Earth orbit, and he has some amazing visual graphics related to in-space manufacturing. So what this is showing is an potential for an in-space manufacturing economy. So what this would require is launch, so the ability to have a reliable way to bring up materials, systems, objects, people up to low Earth orbit, potentially resupply systems if we have satellites, stations, right? We want to maintain those operations. We need the ability to move up in a reliable fashion to low Earth orbit. And then on-orbit manufacturing and processes. So potentially, right now we're using the International Space Station, but potentially we'll move to commercial stations to conduct our manufacturing and also assembly as well. And then use of our in-orbit environment and re-entry. So use of our in-orbit environment, whether it be a station, having processes there, human presence, robotic presence, that would enable an economy. Asteroid mining as well, in-orbit utilization, right? Utilizing and extracting important and very valuable minerals that we would use in terrestrial markets. An important piece of that is re-entry, and this is an area that still needs a lot of work and investment. There are companies that are dedicated to re-entry systems that we're seeing coming into the startup landscape. And so re-entry technology, bringing things back to Earth if we're not going to use them in either space missions or lunar missions, et cetera. So we would bring products back to Earth, and maybe we would bring semiconductor products back to Earth for use in emerging applications such as AI and quantum. What if we had our AI supercomputers of the future built from these advanced non-silicon materials? As you may know, silicon technology is hitting a wall. Power density is becoming an issue, overheating. As we make smaller and smaller transistors, that's going to limit our computation speed. And so we need to look at materials that are made from non-silicon formats, such as diamond or silicon carbide, gallium nitride. These are non-silicon materials that are very challenging to make here on Earth because they suffer from defects, and they also suffer from the inability to grow in very large formats. So maybe one day our AI, our supercomputers will be made from chips that were manufactured in low Earth orbit. So moving beyond, so let's flash to 25 years, around 2050. The cost to launch 1 kilogram to low Earth orbit will be, it's approximated to be $10. So when people say to me, Debbie, that's too expensive to grow materials in space, 25 years from now, cost is not an issue anymore. We're going to have sustained operations. And what is it going to look like? The in-space economy in low Earth orbit, lunar, Mars, and beyond. What do we need? We need, again, sustained up mass and down mass, sustained operations. We also need reliable communication, safe and reliable communication. We also need autonomy. So this really paves the way for new types of spacecraft, robotics. It's a very exciting time to be an engineer and scientist. And then moving to Mars as well. How are we going to sustain human life in these new types of environments? And in addition, asteroid mining, which was mentioned in the earlier talks, how do we use and extract resources and bring them safely back to Earth? And with all of this activity, we need policy and diplomacy. This is why I'm really glad to be here at GESDA to have these wonderful conversations around this type of future endeavor. Not only do we need the science and technology, we need the policy that enables the access to the resources. We also need to think about the ethics and that we conduct this work in a very humanitarian way and together as an international community. So the outlook for the future is coming back to the beginning. Making materials in space is not science fiction. We've actually done it in the early 70s, and there are groups and companies that are looking to do that again in the future. And I want you guys to stay tuned for our next mission that will be aboard SpaceX 31 later this year. We'll be growing metal organic framework crystals and studying their properties once they return back to Earth. So thank you.
Thank you very much, Debbie. We're going to take some questions. Please raise your hand if you would like to ask something about space manufacturing. Debbie, since I introduced you and I said you were doing hardware for Venus, I need to know, what is the Venus grade technology? Like, what do you have to do to send something to Venus?
To send something to Venus, it cannot be made from silicon because silicon becomes noisy from an electronic perspective at elevated temperatures. So I've used gallium nitride, which is a high temperature material, and we've tested our circuits in the NASA Glenn Venus simulation chamber in Ohio, Cleveland, Ohio, and it lasted for 11 days. So we're very excited about that. At 400 yep. Mm-hmm.
Sorry, in a few years, when it's cheaper to send people to space, we can send teenagers who are addicted to TikTok, we can send them to space. Their phone is going to stop working, and then they
you don't want to send them to Venus because it's high temperature. It's too hot there. They won't survive. But other places.
So please raise your hand if you have any question. I'll give you. Okay, we have the microphone is coming. Very quickly, Debbie. So you mentioned that the interest of producing something in space, that there are some things that can only be built there, right? And these crystals are one thing, and you believe that they're going to be useful as a post-silicon way to do transistors. Are there other types of materials or objects or devices that you think are going to be available
Absolutely, yes.
Only through space manufacturing?
Absolutely. So again, we're subject to gravity, so there may be materials out there that we cannot synthesize here on Earth. People have also looked at growing glass fiber, so fiber pulling, where you have a very high quality index of refraction, and so you have higher optical efficiency. Semiconductors is an example, but also biomaterials and biomedicines. So you can think of creating new materials and discovering new materials by moving to low Earth orbit.
We have our first question here.
Yeah, thanks a lot, Sabine Gollner, scientist, deep sea scientist. would have two questions. One short one, are there any calculations on carbon footprint when it comes to factories in space? And the second one would be, do you think that there could be any new materials developed in space that would basically replace the metals currently mined on land?
Yes, very good. So for the carbon footprint, absolutely, we want to not have an impact on the low Earth orbit environment as well. So just as we have the International Space Station that is a closed-loop systems, we would have to develop a way to bring the waste products or reuse the waste products in the processing. So we want to have a clean, zero waste type of process. That's very, very important. And also selecting materials that are efficient to grow and also might reduce the carbon footprint that we create here on Earth. So the second question, if you can repeat it one more time. Oh, new materials, yes. Metals, yes, absolutely. So, of course, mining new types of materials or materials that are not of abundance here on Earth is something that's attractive. Refractory metals, there are metal alloys that are very complex that have more than 3 elements in them, and when you start to alloy them, it's really complicated here on Earth. And so creating ternary plus metal alloys that opens up a new possibility if we move to the microgravity environment, and that's because of the mixing, the sedimentation, and the buoyancy. So creating new alloys that can overcome some of those mixing interactions during growth. Absolutely, that's one benefit of microgravity as well.
We have another question here.
Thank you. Thank you for. Is it me?
I don't.
Excuse, sorry, I'm sorry.
I was couldn't
person
find
who's
you.
going to bring the microphone after, so we have Mahaten.
Margareta Jeniek, Horizon Group based in Geneva. What is the most exciting application that you see for this right now? So also a two-part question. One is what's the most exciting application, and the other one, what would you consider the biggest risk of this work as well?
Yeah, absolutely. The most exciting application for me personally, I'm interested in semiconductor chips and the ability to create large format wafers, so starting substrates that we do not have accessibility here on Earth. So those would be paving the way for communications, for efficient automobiles, conversion, inversion as well, so high power electronics, and then also very passionate about AI as well, although that's not my expertise, but I see a lot of challenges in the way they design supercomputers and also the data centers, challenges in cooling and preventing overheating, which if we move to the non-silicon formats, we might be able to do that in a more efficient way.
Gregory Totten in the Diplomatic Corps of the Order of Malta. We're a 900-year-old humanitarian organization, so not as much in space, but our flag went on the Axiom 3 mission this year.
Cool.
So
Awesome.
a little bit of us went to space.
Yeah.
Two questions. One is, does the debris layer create any obstacles for the full creation of this manufacturing in space ecosystem that you outlined? I know the debris layer seems to be increasing. And then number two,
Right.
the stability of the materials that are created under microgravity, are those intended in part to be brought back to terrestrial use? And is there then any potential for those to have challenges on stability having been created in microgravity? Do they have trouble sort of coming down to Earth?
Right, yeah. So I'll start with the first question related to debris. Absolutely. We have the existing debris layer that hopefully we will deal with and remove by placing some of the larger objects, deorbiting them, figuring out way to potentially recycle them. And that has to be a part of the plan as we place new stations into low Earth orbit. We need to have a plan to deorbit or reuse some of those systems. So moving forward, from what I can tell, that seems to be the plan of implementation, and that has to be developed at the start of the station design and at the start of the mission is that overall cycle. And then to your second question about the reliability, the sustainability of what we manufacture in space. For me, for semiconductors, you're basically sending a rock back to space, so a boule of a crystal material. We're not concerned about reversibility once we get to this Earth's gravity. Of course, surviving re-entry, the shock, et cetera, that's something you would have to develop into the packaging and the re-entry. But I get this question a lot, and someone told me, well, we send humans back to space. So that's probably where the limit. If it were biological materials, then you might have to start to study coming back to a gravitational environment. But humans, that's sort of we know we can return humans safely. So, yeah.
Raise your hand if you have a question.
Yes.
Next one here, and after we go there.
Okay, so far the space was mostly used by actually either countries, public bodies, or military. And now it starts commercial, right, with communications. What you're talking about, this production, it will be, of course, private companies doing it. Now, is there already a governing body? How would you provide licenses, for example? Are you thinking about it? Who can get the license? I mean, and the control also. How is it going to work out?
Right, I'm going to flag our panel from the morning. We have a space lawyer in the house, so no, absolutely. I think right now, correct me if I'm wrong, actually answer. Yeah. I believe it's first to act, but we have treaties, and so go for it.
We have treaties, and we also have national legislation. So anything anyone wants to send up to space falls under the responsibility of a state who has to authorize and supervise it. And so they carry out audits in terms of safety, financial stability, insurance, and so on. So all that is normally covered. And you have licenses, indeed.
Mm-hmm.
And it's a pretty good protection when you think about it. It's like you have a process, you have a patent for a process that only works in space. Like that it's going to be hard for people to copy.
It's really cool. That's the opportunity. Is there's so much opportunity for intellectual property.
We have 1 minute left on the timer, sir. I would appreciate a fast question and a fast answer. Thank you.
Thank you. Jérôme Bellion-Jourdan, Institute for Global Negotiation, an initiative providing support to co-chairs of global negotiation processes. Connecting to the question asked this morning, from where you sit, the outer space can be a replication of conflicts as we have them on Earth, on resources, territory, and everything that we have on the planet. How do you see, how to translate, in a sense, this objective of the Outer Space Treaty, which was that the use and exploration of resources in the outer space should be considered as a province of humankind and therefore a collective as opposed to a competition, which can obviously lead only to conflicts?
Yeah, I think what was mentioned earlier, Lindy, peace, right? We need peace. We need to enable accessibility from an international perspective. I think that these conversations are important to have because if we're going to mine an asteroid or if we're going to have sustained operations on the moon, who benefits from that? It should benefit all of humanity. And so absolutely, totally agree with you. And so I think that we need to have more of these conversations around space diplomacy to ensure that we have these agreements outlined and look to the future of, where these agreements, because we're looking at lunar, Mars, and beyond. So we have to start somewhere. Totally agree.
It's funny when you look at technology and science, it's always the same story. Is that like whether it's quantum or AI or space, like it starts with a technological challenge, and then the questions that technology is asking us have to be answered through diplomacy and not technology in the end. So it's always the same story. Thank you so much for enlightening us about manufacturing in space. That was Debbie Senesky. Please give her one round of applause.
Thank you.
And